cell. You guys are used to battery, okay? But a battery usually consists of cells. A cell is something that was developed around 1800 by a guy named Volta, and there's a certain chemical aspect to it. What we want to know is really generally consists of two different metals. Alright? We'll talk about the electronegativity of metals and whatnot. But metals that are separated by an electrolytic solution, okay, or a paste. So think of salt. Because different atoms want electrons or give them away more than another, you put them in a series of one another between them. One will grab electrons and the other will release them, and that's what sets up your electric potential. The great thing about it is that potential will remain as long as that chemistry is happening. And so you can move cars indefinitely. It's a very huge advancement over, let's say, static chemistry, which is dominant and required to disinfect. Instead of it being build up hydrogen car and so between two metals, the anode and cathode, you know, right? That's the called voltage. Alright, that can convert, you know, this electrical or chemical energy. Alright, great. The battery is a device that consists nothing of one or more cells. So there are two types of cells. We talked about it in rechargeable and non-rechargeable. Well, the technical terms are primary and secondary. Right? So a primary cell cannot be recharged. That is the old school batteries that I grew up with. Right? And basically they were talking cannot recharge it because during its lifetime an irreversible chemical reaction occurs, take place, okay? And therefore the cell is disposed. That's something that you just want to be aware of. We toss them away, they create an environmental issue right now. And the secondary cell is designed to be recharged. Okay? Because you can reverse the chemistry. Examples, car batteries are a good example of rechargeable batteries to a certain extent, and then lithium-ion batteries you can find in a lot of cordless power tools, rechargeable batteries for phones, laptops, etc. Alright. Now, regardless of whether you're a primary cell or a secondary cell, they all have a property called charge capacity. This is something we haven't talked about quite yet. And so you don't usually see this on as a number on the battery. It's on some of them, but it's a measurement of how much charge that can flow before the cell stops working. And so the amount of charge that flows, or that you have stored, depends on two things. It depends on how much power you want to deliver and how long you deliver it. Okay, so that gives rise to a measurement called an ampere hour or amp hour. Okay, so charge capacity is usually measured in amp hours, and if you think about it equation-wise, ampere is current, and hour is time, and what is current times time? Same as well, that's nothing more than charge to do. Okay, so if we have 1 amp hour of charge stored in the battery, we can ask, well, how many coulomb charge is that? That's pretty straightforward, right? 1 amp is that, an hour is equal to 600 seconds. So we multiply those two, we get 3600 amp seconds, which is equal to 3600 coulombs. Alright, so we'll get an application a little bit where I'll have you try one where we're given that value for battery. You can predict how long it'll last depending on how you use it. Alright, so this is what we did in class, and that's how you connect batteries. Alright, when you connect batteries in series, we already said that's positive negative. We set it to EMF add. Alright, so this is something that keep in mind. And when connected in series, but positive, negative, EMF subtracts. And this is how the secondary cell is recharged. So that's something you want to be able to describe. That if I take let's say one cell that looks like that, and I take, let's say, a secondary cell. Okay, so this is a secondary, so this is recharged. And let's say this is 10 volts. this is, let's say, 6 volts. What we'll get is current to flow this way, all right? And that goes against it, and that will recharge the battery. So the net voltage across here is negative 4 volts, okay? This one being right there. Excuse me, negative 4 across here, 4 volts across there, which will recharge it. And then lastly, what we looked at is a little less common is when they're connected in parallel. Okay, so we do know, and we found out they do not add together, right? So what actually happens is it can be very complicated. But what we find is if we have an ideal source and they are the same EMF, then effectively the EMF is the same as either battery. So if I put 2 6-volt batteries in parallel, I get 6 volt output. If they're different EMFs, roughly speaking, it effectively is the average. That's a little more complicated than that. That's a good approximation. I don't think we actually have to test it out. The reason why we might put these in parallel is to simply draw one. It's more complicated. Look at that and discuss it real quick. So if we have a 1.5 volt battery, a double A outgoing battery, so that's a primary battery, not chargeable. We have essentially EMF is 1.5 volts. And as soon as you plug it in and you draw current, you will see that the output drops rather quickly. So you're rarely going to get the output of 1.5. Instead, you're going to get something between, a little less than that. And you can see it's fairly stable. It's almost just like the light. And then it will drop off dramatically. Again, notice the excess amp power. Now, how quickly it drops in that depends on how much current is going on. In other words, if you get the amperage, it's the power. One problem together. So let's say I have a 12 volt car battery. This is rated for 40 amp hours. How long